Can meshing errors invalidate your FEA stress calculations? Imagine building a bridge or designing a machine part and wondering if tiny mistakes in your computer model could cause big problems later. That's what meshing errors are all about. When you run a finite element analysis, or FEA, the model gets broken into small pieces called elements. These elements help the computer solve complex equations about stress and strain. But if these pieces are not right, your stress results might be off. The size and quality of these elements are super important. If the mesh is too coarse, it might miss important stress details, especially where stress is highest. Think of it like trying to see a small crack with a blurry camera. You might miss it. On the other hand, making the mesh very fine gives more detail but takes longer to run and uses more computer power. The trick is finding a good balance between accuracy and speed. Certain meshing mistakes can really mess up your results. For example, if you don't refine the mesh near sharp corners or holes, you might underestimate the stress concentration there. These are spots where stress tends to pile up. Missing these can lead to unsafe designs. Another problem is stress singularities. These happen at idealized sharp corners where, in theory, stress becomes infinite. In real life, these peaks don't happen, but in the model, they can cause the analysis to give unrealistic results. To fix this, engineers often add small fillets or rounded edges to smooth out sharp corners. Choosing the right element type is also key. Using simple, lower-order elements in complex shapes can reduce accuracy. Higher-order elements can better capture the curvature and stress changes but need more computing power. Incorrectly applying boundary conditions or loads can also make the stress results unreliable, especially if the mesh is poor in those areas. To avoid these issues, engineers do something called a mesh convergence study. They refine the mesh step by step and check if the stress results stay consistent. If the results change a lot when the mesh gets finer, it means the mesh was not good enough before. Using different refinement techniques, like reducing element size or increasing element order, helps improve accuracy. Also, smoothing out sharp corners in the design or adding small fillets can prevent stress singularities. Finally, always check the visual output of your analysis. Look at the deformed shape and stress distribution to see if they look realistic. If you see unexpected stress peaks or strange deformations, it might be due to meshing errors. Remember, good meshing is the backbone of reliable stress calculations. If your mesh is not right, your results could be misleading, which might lead to unsafe designs or unexpected failures. Paying attention to mesh quality and doing proper validation makes all the difference in stress analysis.